All right, so this is linear systems part 2. So last time we described our procedure, our algorithm for solving linear systems. We said it was a great algorithm because computers can calculate it very efficiently, very fast. But we hid a lot of the complications that might appear for these kinds of systems, in that all the problems that we saw last time were specifically kind of manufactured so that there were no complications in the algorithm. All right, so what we're going to do today is take a look at what happens in specific cases where there might be complications, and what those complications mean, and how to deal with those complications when you do see them in the algorithm. All right. Okay, so the way we're going to look at this is we're going to start with a simple 2 equations and 2 unknown problem. Minus x plus 2y equals 5. So this would precisely be a problem that you might have seen last week in a homework problem, right? Solve this, right? And what you could have done is you could use the algorithm that we talked about. Write this as a matrix, minus 1, 2, 5, minus 2, 1, 1, and then done the algorithm to figure it out, what x and y should be. But let's not do that yet, or let's not even do that. Let's take a look at kind of the picture of what's going on when we solve a system like this. All right, what is it that we're doing graphically when we say the words solve this system of equations? All right, solve this system of linear equations. So in order to understand the picture, what I'm going to do is I'm going to rewrite both these equations so that they're in the form y equals blah, blah, blah. All right, because that's going to allow me to see the picture more clearly. All right, so for example, this first guy, I'm going to throw the x to the other side. So this is the same as 2y is equal to x plus 5. And I'm going to divide by 2 on both sides. So that's y is equal to 1/2 x plus 5 over 2. All right. The second guy, I'm going to do the same thing. In fact, all I have to do is throw that 2x to the other side, or the minus 2x. I'm going to end up with y equals 2x plus 1. All right. So let me rewrite this system like this. Y is equal to 1/2 x plus 5 over 2. And y is equal to 2x plus 1. So these two problems, the original one and this new one here, are literally the same problem, right? All I've done was manipulate the equations a little bit. All right, why did I want to write it like this? This isn't how we did it last time, right? We never did this kind of rewriting. But the idea here is, if you look at this guy carefully here, and this guy as well, the second guy as well, these are equations of lines, right? This first equation is an equation of a line. It has slope 1/2, and it passes through the y-axis at 5 over 2. So if this is 5 over 2, the line would look something more or less like that. All right, so this is my first line, y equals 1/2 x plus 5 over 2. Okay, my second equation is a line that passes through the y-axis. Its y-intercept is 1, so maybe something there. And its slope is 2x, so it has a much bigger slope. So maybe something like that, right? And this line here is, let's make it a little more easy to see. This line here is y is equal to 2x plus 1, all right? Okay, what am I doing when I solve the system of equations? What I'm doing is I'm finding x and y that satisfies this equation and this equation. All right. So when I find an x and y, a pair of numbers, x and y, that solve the first equation, what I'm doing is I'm finding points that live on line number 1. All right. So any pair of numbers, x and y, for example, x equals 0, y equals 5 over 2, that represents this point on the line. All right. Another one, x equals 2, y equals, when x is 2, y is 7 over 2. That represents another point on this line, all right? Represents this point on the line, all right? So every point that satisfies the first equation is a point on the line, all right? Okay, same way, every point that satisfies the second equation, any pair of numbers, x and y, that satisfies the second equation is a point on the second line, all right? So when I solve the system of equations, what I'm solving for are x and y so that they satisfy both equations. And what that means in terms of the picture is that I'm looking for a point that lives on both line number 1 and on line number 2. All right. So in terms of the picture, what I'm looking for is that point right there. Okay. So when we do this solving procedure, or whatever solving procedure to solve this system of equations, 2 equations and 2 unknowns, we're solving for this point right there, right? This is what we're solving for. Okay, and if we did this procedure, this turns out to be the coordinates 1, 3. And so if we actually solve this equation, it would be x equals 1, y equals 3. All right, and so that x equals 1, y equals 3 means the 2 lines intersect at 1, 3. All right. Okay, so we're solving for intersections of lines when we solve 2 equations and 2 unknowns. All right, now most of the time, what's going to happen is if you do have 2 lines, in other words, if I just close my eyes and randomly pick numbers, right? Minus 3x plus 4y equals 10, 2x minus 10y equals 59, right? Then this will represent 2 lines, something like this and something like that, perhaps. And when you solve, you're going to find the intersection, right? And so generically what happens is 2 lines will have exactly 1 intersection. But let's see what happens if I set up this equation, if I set up a system of equations in a particular way. So if I look at 2x plus 4y equals 5 and 3x plus 6y equals 1, let's do this, let's solve this system of equations using our procedure that we learned last time. So 2, 4, 5, 3, 6, 1, like that, all right? We're going to use this 2 right there to clear everything underneath it. In other words, to clear that 3 as our first step. So that means row 2 is going to be changing. And the way it's going to change is we're going to multiply minus 3 over 2 row 1, and we're going to add it to row 2. All right? So in our next step, we're going to end up with 0 there. And then I'm going to multiply minus 3 halves to 4 and add it to 6. All right? So minus 3 halves times 4 is going to be minus 3 times 2, which is minus 6. Minus 6 plus 6 is 0. All right. Okay, let's do the same thing with the 5. 5 times minus 3 halves is minus 15 halves, right? Minus 15 halves and then plus 1 is going to be minus 13 halves. So this is going to be minus 13 halves. All right. Okay, now there's nothing left to clear under the 2. So our next step would have been to go to the next line and clear things under that. But this has a 0 there. There's nothing left to do. All right. So normally what we would do now is to convert this back into a system of equations and then solve it. So let's do that. This bottom system is 0x plus 0y equals minus 13 over 2. The first one is 2x plus 4y equals 5. All right. Now let's take a look at this. 0x plus 0y, that's just 0, right? So this system is actually the same as 2x plus 4y equals 5. And the bottom one is actually 0 equals minus 13 over 2. Okay, what does that mean? That means that we have no solution because 0 is never equal to 13 over 2, right? This is never, right? In other words, when I say never, I mean no matter what x and what y you give me, this second equation will never be satisfied because it doesn't even involve x's and y's in it, right? So this bottom line is never true. And so what that means is that there's no solutions. Okay, so when you reach the end of your procedure, the procedure that we talked about last time, you convert it back to a system of equations and you see something that, an equation that can't be solved, right? This never right here, that means there's no solutions. All right. So you didn't see that last time because again the problems were all set up, so it never happened. But today we're examining specifically this type of complication. All right. So what's happening here in terms of the picture? Well, if I think about my two original equations, 2x plus 4y equals 5, if I write this top one, this first one as a line, this is going to be 4y equals minus 2x plus 5, which is y is equal to minus 1/2 x plus 5/4. All right. The second one is going to be 6y is equal to minus 3x plus 1. And so y is equal to minus 1/2 x plus 1/6. All right. So actually what's going on is this first line is a line with slope negative 1/2, and it passes through the point, the y-intercept is 5/4. So the first line is like this, it has slope negative 1/2. All right. The second line also has slope minus 1/2, but it passes through 1/6. So the second line actually lives here, right? But they have the same slope, so they're actually parallel. And what happens is they don't touch, right? And that makes sense because when we're solving these systems of equations, we just said we're finding the intersection of the two lines. And when you have this situation where you see the answer being never, effectively what that means is my two lines are parallel. All right. So this down here is the picture of what's going on when you have exactly this type of equation with exactly this type of never complication. All right. So that's the first situation. And again, that's where you have no solutions because what you're solving for is the intersection of lines. And these two lines happen to be parallel. Okay. Now let's do a different problem. Let's take a look at 2x plus 4y equals 5 and 3x plus 6y equals 15 over 2. All right. So let's solve this. And let me do this in exactly the same way. And in fact, if you think about this, this is almost the same problem as we just had. 2x plus 4y equals 5. 3x plus 6y, before it was equal to 1. Now I've changed it to 15 over 2. All right. Okay, but let's do the procedure again anyway. Row 2 equals minus 3/2 row 1 plus row 2. All right. 2, 4, 5, those don't change. The second row, when I do this, I'm going to get a 0 here. When I do this, I'm going to get a 0 here. And then when I do this last one, I'm going to get minus 15 over 2 plus 15 over 2. All right, 0 as well. Okay, so this is actually going to be different because when I transform this back into a system of equations, I have 2x plus 4y equals 5. And down here, I have 0 equals 0. All right. Okay, what does this mean? Well, 0 equals 0 is not a problem compared to what we had before. Before we had 0 equals minus 13 over 2. That was bad because 0 is certainly not equal to minus 13 over 2. But down here, 0 equals 0, this is always true, right? So in effect, what this means is that this second equation is meaningless. We might as well just erase it. It doesn't provide anything to our problem, all right? So in effect, this problem only has one equation, all right? And so what's happening is there's going to be an infinite number of solutions because these two guys actually describe the exact same line, right? And let's actually see that. This first one was y equals minus 1/2 x plus 5 over 2. Let's solve the same thing for the second one. We throw the 3x to the other side. 6y equals minus 3x plus 15 over 2. Sorry, that was a 15 over 2. Sorry, 5 over 2. It was correct. And down here, when I divide by 6, I get y equals minus 1/2 x plus 5 over 2, right? So equation 1 is a line. Equation 2 is literally the same line, right? Minus 1/2 x plus 5 over 2 for the first one. Minus 1/2 x plus 5 over 2 is the second one. So what we're solving for here is the intersection of these two lines, but these two lines are actually the same line. So where do they intersect? they intersect everywhere that lives on the line because they're the same line, right? So the solution is going to be every x comma y that live on this single line, all right? In other words, it's every x comma y that satisfies this equation down here, okay? How do we generally write our solution in this case in terms of our system of equations? What we generally do is, what this means essentially is that one of the variables is free to be whatever it wants, all right? And the other variable is going to depend on that first one. So traditionally, our convention is to let the second variable, the last variable, let me say it like that, the last variable. So here I'm listing my variables, right? This column represents x, that column represents y. So the last one is the y. Okay, so I'm going to let the y be a free variable, and I'm going to write the x in terms of y. All right, so my solution is going to be this. Let me solve for x for this equation. X is 2x is equal to minus 4y plus 5. And so x is equal to minus 2y plus 5 over 2. Okay, so x is going to be this. And what is y? Y is free. All right. In other words, y can be any number. All right. So how do I actually use this? Let's say I want one solution to this problem, right? Then what I do is I pick any y I want because it's free. So let's say y equals 0. And then x has to be, once y is determined, once I've chosen y, x is determined, right? X has to be minus 2 times 0 plus 5 over 2, which is 5 over 2, right? So if I just wanted one solution, that would be x equals 5 over 2, y equals 0, all right? But there's more. There's an infinite number because every y that I choose will correspond to a different x solution, okay? So let's just do y equals 1. That's going to be another one. And that's going to correspond to x equals minus 2 times 1 plus 5 over 2, which happens to be 1/2. All right. So another solution would be 1/2 x equals 1/2, y equals 1. All right. And as you can see, right, I can choose y to be anything. Y equals minus 1 is going to give me another solution. Y equals 10 is going to give me another one. That's what we mean by the word free, right? Y is free to be anything it wants. But once we've chosen y, that means x is determined to be some other number. All right. So you can see infinite number of solutions because y has an infinite number of possibilities. All right. And again, this all makes sense because we're searching for the intersection of two lines, and those two lines happen to be the same line, so they lie on top of each other. And so their intersection is actually every point that's on that one line. All right. Okay. So maybe a good exercise for you right now is to do this except with three variables, x plus 3y plus 4z equals 3, 2x minus y plus 2z equals 2, and x minus 4y minus 2z equals 8, right? Solve this. And again, we use the procedure that we learned last time, and then we're going to hit a complication. And that complication, depending on what it looks like, determines how many solutions this has. But before we do that, let me explain what we're doing here, right? So before we were solving two equations and two unknowns, and we interpreted that as finding the intersection of two lines in the plane. So here what's happening is we're finding let me say it like this. So here, when you have three variables, we're actually working in space. So x, y, z. And what we're doing is each of these guys represents a plane in space, like a flat plane, all right? So maybe this first one looks like that. The second one maybe looks like a plane like that, right? And then the third one looks like a third plane, okay? And what we're doing is we're finding the intersection of three planes. All right. And what's going to happen is, in general, there's going to be one solution, but sometimes there will be no solutions, just like with the line situation. Sometimes there'll be an infinite number of solutions, just like the line situation. All right. Okay, but in terms of pictures, we're finding the intersection of three planes. Okay, so maybe pause and figure this one out. And then I'll reveal the answer, and then I'll change it a little bit and then do another problem. Okay, so hopefully you've done this one now. What happens ultimately in the end is you'll see that when you convert this back into a system of equations after doing the algorithm we talked about last time, you'll see an inconsistency, right? You'll see whatever, 10 equals 0, and so there's no solutions. Okay, so what happens here is that these three planes, they don't all intersect in one point. All right, so it's similar to the two parallel line problem that we just talked about. Okay, now let me talk about the same problem, except let me modify it a little bit. And we'll see the other situation pop up. And because you've already done most of this just with a different number, all I've done actually is changed this 8 into a minus, into a minus 1 down here. All right. So because you've already done it, most of it, I'm just going to reveal what happens if you actually finish the procedure. What you end up with is, so let me put ... is something that looks like this. X plus 3y plus 4z equals 3, minus 7y minus 6z equals minus 4, and 0 equals 0. All right. So previously, hopefully, when you did this one up here, you got something like 5 equals 0, right? Which doesn't work. But now we have this 0 equals 0 situation. And what that means is that this equation tells me nothing. And so ultimately, I really only have two equations. All right. And so this is similar or analogous to the two lines situation where two of the lines were the same. All right. In this case, because it's three-dimensional, it could be a little more complicated than that. You can have three planes intersect, but the planes, two of the planes are not the same, right? So you could have a plane that looks like this, and then another plane that intersects in the same line, and then a third plane that intersects in the same line, like that, right? So this situation does not necessarily mean that two of the planes are the same, all right? So 3D is actually a lot more complicated than 2D, but the rough idea of what's going on is the same. Okay, so what does this mean? This means, again, that we're going to have an infinite number of solutions, and so that means we're going to have a free variable, and we always choose the last variable to be free, and in this case, it's going to be z. All right, so z is equal to free. Okay, and what that means is we go to this second equation and we solve for y. All right, so that tells me, let me label these. Let me call this equation 1, equation 2, right? And again, we're still going from the bottom up, just like before. We work with equation, well, in a way, equation 3 tells me z is free. Equation 2 is going to give me y. All right, sorry about that. So minus equation 2 tells me minus 7y minus 6z equals minus 4, right? Z is free, so I need to write y in terms of z. So this tells me minus 7y is equal to 6z minus 4. Dividing by minus 7, I get y is equal to minus 6 over 7z plus 4 over 7. Okay. All right, so that's my answer for y, right? Remember, it has to be in terms of z. Okay, how do we get x? Well, we just go up one step, just like we did last time, except this time, every time we see a z, we leave it as is because z is free. Every time we see a y, we substitute the y that we just found, and it'll be in terms of z. And then that will allow us to solve for x, right? So we have x plus 3y plus 4z equals 3. That's equation 1. Now I put in my y, which is 3 times minus 6 over 7z plus 4 over 7, and then plus 4z equals 3. All right. And now I solve for x. Let me clean this up a little bit. This is x plus 8, sorry, let me write it as minus 18 over 7z plus 12 over 7 plus 4z equals 3. Let me combine the z's right now. This is x minus 18 over 7 z plus 4z is going to be, when I put common denominators, is going to be plus 10 over 7z plus 12 over 7 equals 3. And so this tells me x is equal to minus 10 over 7z minus 12 over 7 plus 3. And just cleaning that up, I get x equals minus 10 over 7z. And then this is going to be common denominators. I'm going to get 7 on the bottom. 21 minus 12 is 9. All right, so that's my x. Okay, so my final solution is x is equal to minus 10 over 7z plus 9 over 7. Y is equal to minus 6 over 7z plus 4 over 7. And z is equal to 3. So we'll just write our solutions like this. Okay, and again, the interpretation here is that if I want you to tell me one solution to this problem, you would pick any z you like, right? Z equals 0 would be nice and convenient. And that would tell you y and z, right? For z equals 0, y would be 4/7, x would be 9/7. And so one solution to the problem would be x equals 9/7, y equals 4/7, z equals 0, right? If I want you to give me a second one, you pick another z, anything you want, z equals 1, right? And then you plug in z equals 1 to get you y and x. Looks like this would be minus 2/7 for y, and x would be minus 1/7. Okay, and of course I can ask for as many as I like because there's an infinite number of solutions, because z can be any number I like. All right. Okay, so let me just put in quotes here, or let me just emphasize infinite solutions. Okay, so these two problems show us what happens or how to deal with our complications. You're always happy to see the first type of complication because there's no solutions and you just stop the problem immediately, right, when there's no solutions. The second complication is a little more messy because there's an infinite number of solutions, and so therefore you're going to have to work with this generic free variable z. And again, your x and your y's are going to depend on z. Okay. All right. So that's pretty much the situation that you'll see generically. You'll probably see this again in the future if you do the calculus sequence. One of the classes, an entire class, is devoted to working with matrices and working with linear systems or linear equations. And you'll talk about this algorithm that we talked about in more depth. There are some other issues that might arise, especially when you have more variables. In particular, sometimes it's not as obvious how to choose the free variable, but we're going to keep this simple and just do problems which are relatively straightforward. Okay, before we end this, let me talk about the most general case. All right, so far, all the problems I've written down, the number of equations, so far, number of equations is equal to number of unknowns. All right, let me call the number of equations m, and let me call the number of unknowns n. All right, so far we've been only talking about problems, we've only worked with problems that have 2 equations, 2 unknowns, 3 equations, 3 unknowns. In homework, there was 4 equations, 4 unknowns, always the same number. All right. Now, what happens if you want to solve a system where the number of equations and unknowns are different, right? So far we've worked with this, but what if you had fewer equations than unknowns? Or what if you had more equations than unknowns? How do you deal with those? How do you deal with these two? So let me write m equals n. We know how to deal with that pretty much, right? So how do we deal with if you have fewer equations than unknowns? So the idea here is, let me do it down here. So if m is less than n, then what you have is maybe a whole bunch of unknowns. So maybe 2x plus 3y plus 4z equals 10. And let's say x minus y plus 10z equals 5, but no more, right? So I have 3 unknowns and 2 equations, so fewer equations than unknowns. How do I actually solve this? Well, one way you can do it is just pretend there's another equation, 0 equals 0, and solve it just as we did before. Okay, so you would do this, 2, 3, 4, 10, 1 minus 1, 10, 5, 0, 0, 0, 0. All right, so this bottom row is all resolved. You never have to touch it. And so you just do the algorithm that we talked about. And then when you translate it back to a system of equations, this last one will be 0 equals 0. And then that means you're probably going to have a free variable. All right. Okay, so the point here is that number one, if you have fewer equations than unknowns, you can still solve it in the same way that we've been solving equations. And point number two is that because this last row is all zeros, it means that usually there's going to be a free variable. All right. Okay, I'm going to say a couple more words about that in a few minutes, but before we move on to the m bigger than n case, typically in practice, when we have only 2 equations and 2 equations and 3 unknowns, we don't bother to write the last row. We usually just write 2, 3, 4, 10, 1 minus 1, 10, 5, and we just work this way. And the goal always being, you work with this, clear everything under it. Next, you would work with this and clear everything under it, but there's no more, so you stop there. All right? Okay. But if you're not comfortable with that, just solve it the way we have been solving by writing a row of zeros, and it'll be exactly just literally the same procedure. Okay. What happens if m is bigger than n? So if you have more equations than unknowns. So for example, 2x plus 3y equals 10, 4x plus 5y equals 9, 3x plus y is equal to 15. All right. Okay. In this case, what's going to happen is, or the way you can think of this is, again, if we do know how to work with same number of equations as unknowns. So what we can do is convert that into 3 equations, 3 unknowns, by just pretending there's a variable z, right? And pretending that the coefficient of z is 0, right? So this is the same as 2x plus 3y plus 0z equals 10. 4x plus 5y plus 0z equals 9. 3x plus y plus 0z equals 15. And this down here is a problem that we already know how to do, right? We would write this 2, 3, 0, 10, 4, 5, 0, 9, 3, 1, 0, 15. And we would do our little procedure, all right? And what's generically going to happen is that this 2 is going to clear that 4, it's going to clear that 3. And then whatever is left here is going to clear the thing underneath it. And because there's no term right there, because this one's always 0, right? No matter what you do, no matter what operations you do, this last term is going to stay 0 forever. The second to last term is also 0. That 0 is also going to stay 0. And so generically what's going to happen is you're going to end up with something like 0 equals some number here, which is not 0, right? And so generically there'll be no solutions. Okay. So this is how one way you could do it, but typically the way we actually write this up is just 2, 3, 4, 5, 3, 1, 10, 9, 15. And what we do is we don't bother to write the last row of zeros. We use the 2 to clear the 4 and the 3. And then after that, we use whatever number is here to clear that number down there. And then there's nothing else to clear. So what you're going to end up with is a 0 here and a 0 there. And almost certainly, this guy here will not be 0. It could just by luck be 0, but generically it's not going to be 0. And if it's not 0, that means there's no solutions. All right? So what you can see here is that when you have more equations than unknowns, usually there's no solutions. All right? When you have fewer equations than unknowns, usually there's going to be an infinite number of solutions. And usually when there's the same number of equations as unknowns, there's going to be a finite number of solutions. All right? And generically, in terms of math problems, this is very frequently true. All right? Even if the equations aren't linear equations, this is very frequently true. All right? So it's a general principle in math. All right, and again, in terms of our discussion of intersections of lines, all of this makes sense, right? Because here, this m less than n means I only have one equation, so I only have one line, right? So I'm looking for points on one line. So there's an infinite number of solutions, right? Because each line has an infinite number of points. But the second one down here, I'm looking for the intersection of 3 lines, right? If m is so in this example here, right? That's a line, that's a line, that's a line. If I try to solve this, what I'm solving for is the intersection of 3 lines. But the problem is, if I close my eyes and I pick 3 lines, right? They're not going to intersect in one point, right? These 2 lines intersect there. These 2 lines intersect there. These 2 lines intersect there. But there is no one point where all 3 touch. Right? And that's what you're looking for when you solve these system of equations, right? A point where all of them touch. So generically, that's the picture reason why you expect there to be no solutions, right? Again, if I close my eyes and I draw 3 lines, there's pretty much no chance that they're all going to go through the same point, okay? All right, so that's a very quick introduction to the study of linear systems. And again, if you do take the calculus sequence, if you do take all the calculus sequence, especially if you're going to be an engineer or a STEM major, then you're going to see this again, and you're going to see it in a more advanced setting. But this is the core ideas behind what's going on.